No questions.
Anyone else? Okay. In that case, let us discuss the exciting topic of rotationally symmetric systems. Okay. So in a previous lecture, we saw that, when we rotate a system, that is, we translate it on a circular path. So this is not a very good circle. So this is a circular path. Okay. When we rotate a system by some angle, say alpha. So this is my angle alpha. So then what happens to the state of the particle? That is the wave function. Okay. So if this direction coming out of the page is n, then the wave function gets changed by multiplied by a unitary operator, which we can say, we can u alpha n, we can specify it. And this has the form e to the power minus alpha. There's an I here, I alpha n dot L, right? So this is a unitary operator. So if this is a unitary operator, what does that imply for this operator, n dot L? So what kind of operator is this, if this is going to be unitary?
Hermitian.
Okay. Did others get it? Why this has to be Hermitian for this to be unitary?
Yeah, I got it now. Yeah.
Okay. So except for Shujat and Nahi, can someone tell me what unitarity means? What does it mean for an operator to be unitary? If U is a unitary operator, what conditions, what is it? What does it have to satisfy? We all know that what Hermitian is. Hermitian is, if I take its dagger, it'll be the same operator. That's Hermitian. What about unitary? If I take the dagger of a unitary operator, what do I get?
Wasn't it u minus 1?
Great. So unitary operators satisfy this equation.
Wait, by minus 1, like, is that inverse or like u and then 1 subtracted from that?
Inverse.
I thought subtracted. Okay.
Yeah. No, it's not subtracted. It's in the exponent.
That's okay.
Okay. So unitary operators have the wonderful property that their inverse is given by the Hermitian conjugate. Okay. And now if I can write a unitary operator in terms of e to the power I, some real number times some some operator a, then we are asking u to be unitary. That means u of dagger needs to be u inverse. And we can ask, what is the inverse of u? If u of inverse, it's easy to see that u of inverse needs to be this thing. Because then u inverse will be e I alpha. Because an operator will always commute with itself, we can write this like that. Okay? Because, the exponents will add like numbers. So now, does U dagger give me U inverse? Well, if I start with U and take its dagger, then I get on the right-hand side Ui alpha A, and this is a dagger. So I becomes minus I, alpha is a real number, and A becomes a dagger. So for this thing to be equal to U inverse, we see that A dagger has to be equal to A. Right? So we see that for a unitary operator, A needs to be Hermitian. Okay, and this is what we have here. We have a unitary operator, which implements rotation on a state, and its form is given by exponential of I times a real number, a parameter, times a Hermitian operator. Okay, so this is a form you need to understand. If you're going to do physics, you need to understand this form for the rest of your life, okay? Okay, now let's come to rotational invariant system. So if I apply that rotation on some state psi, so I'm applying U on some state psi, so U alpha n, so I get another state psi prime. But rotational invariance means that the energy remains unchanged. Okay. So that means that if I compute the expectation value of the Hamiltonian with respect to the changed state, that should be the same as the expectation value of the Hamiltonian of the state before rotation. So we can write this equation now as H. What is psi prime? Psi prime is U alpha n acting on psi. And then what is the bra of psi prime? It'll be psi, bra of psi acted on the right by U of dagger alpha of n hat. On the right-hand side, I have psi H of psi. Now, this equation is valid for any arbitrary psi by assumption, because we did not make, we were changing any arbitrary state, we were rotating it. And we were saying that because it's rotationally invariant, the energy should be the same, under rotation, regardless of what state we started with. So that means that this relationship has to be true as an operator relationship. So this means that U of dagger alpha n hat H U of dagger alpha n hat has to be equal to H. So for rotational invariant system, this has to be true. But this thing is nothing but U inverse. So if I multiply the left of this equation by U, so if I left multiply this equation by U, and right multiply this equation, okay, actually what I'm going to do is something different. What I'm going to do is that I'm going to take alpha small, okay? So that we can express U as a power series in alpha. So the first term of U would be A1 because it's an exponential. And then we will have I of alpha n dot L. Then U of dagger, which is equal to U inverse, that will have the expansion of 1 plus I alpha n dot L. So if I look at this equation up to order alpha, so up to order alpha, then I get that this equation implies that H will commute with alpha n dot L. But n, alpha, all of these things were arbitrary. So this is equal to 0. That's what this equation will become. But alpha and n, the n direction was arbitrary. Alpha was an arbitrary small angle. So for this to be true, H will have to commute with all the components of L. Right? So rotationally invariant system must satisfy this relationship. Okay? This is what we were trying to get at.
Sir, so the position of the state doesn't matter as long as the energy is same. It's all right. Like
right.
Okay.
So, I mean, the thing is that there could be a state for which this is true. There could be a special state for this to be true.
Mm-hmm.
But we are not assuming that special state. We are saying that this has to be true for any state and for any rotation.
Okay.
If this is true only for a particular special state, then we cannot do this. We cannot go down and claim that this is true. So if it's true for any special state, we cannot say this is a rotationally invariant system. Okay?
Yeah, okay.
And like I will give you an example of such a system and such a state. Okay?
Okay, sir.
Okay. So this is what it means for rotational invariance. So okay, let me make a comment. For rotationally invariant, comment number 1, systems, H must commute, its H must commute with L. Okay, so I've done this for orbital angular momentum, but it also holds for spin angular momentum, right? And therefore, we can generalize this that, in general, rotational invariance implies that H commutes with J. J can be L or it can be S, it can be the sum of two, okay? Okay, any questions?
No, sir.
Anyone else?
Sir, since it's Hermitian, since it's Hamiltonian or energy, can we say that it applies for momentum as well? That the commute momentum
no.
squared, I guess.
Yeah, momentum squared, but it can have a term which is has a potential, right?
Yeah, the potential term. So that negates the effect.
So, in general, you cannot make a statement like that. You have to have assumptions about the potential as well.
Yeah, okay.
Okay. If the potential and the momentum and the kinetic term are separately rotationally invariant, of course, the whole system is rotationally invariant. And that is precisely what you get both in the harmonic oscillator as well as the hydrogen atom.
I see, yeah. Okay.
Okay, so so for example, a system doesn't have to be rotationally invariant around all the axes. So for example, if the system has rotational invariance in the xy plane, then it'll just rotate around the z-axis. It'll just satisfy this, okay? So this is a reduced rotational invariance, right? Or rotational invariance in the xy plane.